So welcome everybody to this afternoon's edition of the Heidelberg Joint Astronomy Colloquium. Now, you know that in recent weeks we've been looking a lot at very compact, dense objects such as neutron stars, black holes. Now we're going to go completely the opposite. We're going to the diffuse universe, and we're very privileged to have as our speaker today one of the persons who has recently promoted a lot of widespread interest in that topic, namely Pieter van Dokkum. And Peter's host is Diederik Christian, who's making a reappearance here now. So I hand over to Diederik for Peter's introduction.
Thank you, Richard. Yes, it's a real privilege and honor to have you here, Peter, today. After all our semesters that we tried, it is wonderful that it worked out this time. And of course, it's unfortunate that it's virtual, but I really hope that we'll be able to welcome you in person the moment that is possible again. Peter has a very, very rich and impressive CV. In 1999, Peter received his PhD cum laude from the University of Groningen. After that, he obtained a Hubble Fellowship at Caltech and subsequently a Spitzer Fellowship, which he also held at Caltech. And then in 2003, Peter became an assistant professor at Yale University, where in then 2005 and 2007, he went on to become associate and then full professor. Between 2011 and 2016, he was the chair of the Department of Astronomy at Yale. And since 2012, he holds the Sol Goldman Chair as the inaugural chair holder at the University of Yale. And in addition, he has received many awards, such as the Pastor Schmeitz Prize and the Editing Lecturer from the Royal Astronomical Society. And yeah, as we know, Peter is a world-leading expert on observational surveys of the galaxy population all the way across cosmic history. And in addition, of course, he's the builder of the Dragonfly Telephoto Array. And he's used this to really pioneer studies of ultra low surface brightness and ultra diffuse galaxies. And one of the most, I think, thought-provoking results of these studies has been the discovery of galaxies that are lacking dark matter. And that is what Peter will be talking to us about today. So Peter, by all means, please go ahead. The floor is yours, and share your screen.
All right. Well, thank you very much, Diederik. I'm thoroughly embarrassed now, as was no doubt the intention. Yeah, it's great to be here, even if only virtually, unfortunately. As I said to some of you before, I do plan to visit more often in the future, Heidelberg in person, not just through Zoom. Yeah, so I'll talk about this strange discovery that we made of galaxies that appear to lack any dark matter. It was done with a team of people, obviously, and so this, I'm not going to list everybody, but the central people are up here: Shani Danieli, who's now at Princeton; Zili Shen, who's a grad student at Yale; Deb Lockhorst, who is currently a grad student in Toronto, but is going to Victoria as a postdoc; and then Untitled Chapter, who's also a graduate student at Yale. The work here was inspired and done partly with this Dragonfly telescope that Diederik alluded to. And here's a schematic of the thing. So what we did was we made a telescope out of telephoto lenses, 48 high-end Canon telephoto lenses that are all looking at the same part of the sky. And so you build up a big, big telescope out of many little parts. And the nice thing is they have superb optics, these lenses, very good anti-reflection coatings, and they have this nanotechnology coatings that are quite astonishing. They're also perfectly baffled, obviously, because they have this, they're fully enclosed, and they're lenses, which means that there's no scattered light from mirrors and effects like that. The problem is they're small, but if you combine a whole bunch of them, you start to build up a larger telescope. And so it's effectively a 1 meter diameter f/0.4 refractor. So it's a telescope that you really can't build any other way. It's also the largest operating refractor and kind of the largest ever built. We're still researching that. But if we make it 2 inches larger, then it'll be the largest ever built. So take that for what it is. And the previous ones, of course, were built 100 years ago. Like the Yerkes refractor and things like that. So that's the telescope, and what it can do, Dragonfly. Here it's operating actually at New Mexico skies. This is the back, and we should really tape those little lights actually that are on the back of the telescope. But what it can do is it can take excellent low surface brightness imaging of the sky. It's because low surface brightness imaging is limited by contrast. So you have these very bright stars in the sky, and then you have this faint fuzz that you want to detect. And in conventional telescopes, the bright stars outshine the faint fuzz. So the wings of the stars kind of destroy the signal that you're after. It's also due to flat fielding issues and the small size of CCD detectors and the small field of view of regular telescopes. It's hard to detect things that are very big, bigger than about 20 or 30 arc seconds, in surface brightness, and certainly up to like half a degree. It's almost impossible. But with Dragonfly, we can. And so that was the idea of behind the telescope. And here's the team. So we're having a lot of fun. Is what this is meant to illustrate. So the telescopes are in 2 little domes. At the very end, if there's time, or if people ask about it, I can talk about an upgrade where we're actually going to 6 little domes and a total of 168 lenses. And here's then an image taken with Dragonfly, meant to illustrate its low surface brightness capabilities. So for scale, there's a full moon in the corner. And so it's a giant field, right? It images 6 square degrees in one shot. And this is supposed to be a pretty empty region of the sky. But there's tons of cirrus, that was largely unknown. And the cirrus is, of course, a problem for us because we'd like to see things that are behind the galactic dust. So removing the cirrus is a whole different topic and potentially a whole different talk that would put everybody to sleep. But very important and actually interesting because you can learn about the dust properties of the Milky Way. Most fields don't look like this, but about half the sky, or even 60–70% of the sky has some cirrus or moderate cirrus at these faint levels. The brightest things here are about 25th magnitude per square arc second. So it's really very faint. Okay, now in terms of galaxies, and the galaxy that we'll be talking about a lot today, I just want to illustrate what data from this telescope look like by comparing a bunch of different surveys and public surveys of a particular region of the sky. This region is nice because it has an elliptical galaxy, NGC 1052, a spiral galaxy, NGC 1042, and then this galaxy 1052 DF2, that's this object without dark matter, giving away part of the punchline, but Diderik did that anyway, so I think that's okay. And so you can see a low surface brightness galaxy, an elliptical galaxy, and a spiral galaxy here. And this image is from decals. Okay, so public 4-meter data, very good quality from CTIL. This is Sloan at very high contrast. So this shows you the faintest emission that Sloan sees. And there's a whole bunch of things here that are sort of interesting to remark upon. You can see the scan direction of Sloan, it's drift scanning, and that leads to interesting things happening with the star on the left, that bright star. But in general, it's actually quite good, Sloan, for a low surface brightness work. It's just not very deep, small telescope and about 50 seconds of exposure time, but quite good. This is Panama Sky Survey, excellent for low surface brightness work, really, really excellent. Photographic plates are hard to improve upon, actually, when it comes to flat fielding and things like that, but not very sensitive. Note, though, that the 1052 DF2 object is visible in Palomar Sky Survey plate, and it's not all that faint, really, in that context. Then this is Pan-STARRS, pretty hopeless for low surface brightness work. It's not meant to be good in that regime. It's meant to be good for point sources, but it shows you the difficulty with small detectors, right? To image a large area of the sky. This is about 1 degree on the side, and because you get this patching effect of the flat fielding errors, etc. And here's decals, the same image as I started with, but then at low surface brightness. And here, again, there's issues, and the issues now come from sky subtraction. The large objects have a lot of faint emission, and that what happens is if you apply sort of standard fitting to the sky, you tend to over subtract, and you get these halos around objects where the light is over subtracted. You can fix this to some extent, but the problem is then flat fielding errors and other issues with the data are not corrected for. So you kind of have to make a choice whether you go for your observing strategy, really, whether you go for low surface brightness emission or point sources. And pan-stars is optimized. Decals is optimized for compact things. And here's Dragonfly. And so much more light is detected out to a much larger radii, as you can see. The spatial resolution, though, is extremely poor. Right, so that's the price you pay going to these telephoto lenses. The spatial resolution is about 5 arc seconds for without max. So you get blending of things in the background, and it becomes hard to distinguish low surface brightness emission from clumps of other galaxies and stars. On the other hand, you have this superb sensitivity to a large-scale structure. So all these telescopes have their pluses and minuses. Now there's a trick you can do. You can take high-resolution data like that of decals, and then make a model for all the high-resolution things in the image, all the stars and all the little galaxies, etc. Convolve that with the point spread function and subtract it. So we developed this method to do that automatically called multi-resolution filtering, and that's been done. That we do that standard on every frame we have, making use of the Sloan data and the decals data, etc. And then you clean up, all these stars and other things that sort of blend together. And you get a nice low surface brightness image. And yeah, just for comparison, decals is far deeper and with the 4 meter and beautiful data. But when it comes to low surface brightness emission, you really miss a ton with that telescope. And in general, it's hard to achieve what Dragonfly can achieve. Anyway, so what did we discover then with this telescope? And one of the things that we discovered fairly early on, and that in hindsight didn't really require Dragonfly special abilities, because these things are fairly easy to find, as happened like very shortly after, are these ultra-diffuse galaxies. And so we found them when we looked at an image of the Coma cluster that we just took for fun, why not? And there are many of these blobs in the direction of the Coma cluster. So the Coma cluster is the nearest rich galaxy cluster in the sky. It's much richer than the Virgo cluster, which is even closer to us. Coma is very massive, but it fits nicely in the Dragonfly field of view. So we took an image. And there's these little fuzzy things. This is Dragonfly data, and you can see the scale. This is 37 arc seconds on the side. So these things are really quite big. And initially, we thought they were dwarf galaxies in the foreground, or we didn't really know what they were. But it turns out that they are actually at the distance of Coma and intrinsically very large. So these are galaxies that have the sizes similar to the Milky Way, so several kiloparsecs in their half-light radius, but far fewer stars. So 100 to 1,000 times fewer stars. Let me just illustrate in one of them. This is the Dragonfly data. And then here is an image of the same area of the sky with HST. Okay, now in the smudge you see, or Richard said it looked like a thumbprint on the monitor. So I trust that that's what you're seeing. Something there, hopefully, but not much. That's the galaxy. And so this galaxy, Dragonfly 44, as it's called, has a half-light radius of 4.5 kiloparsec, which means it's actually bigger than the Milky Way by a factor of 1.4 or so. But it has 200 times fewer stars. It's just a fuzzy blob, essentially. And there are many of those. This thing is not alone. And so we found 48 with Dragonfly back then in 2015 of these galaxies. We thought that was a lot. 2 months later, there was a paper by Koda et al. Using Subaru archival data. They went back, found all our galaxies, and then found about 1,000 more. So they wrote a paper saying 1,000. We said 48, they said 1,000 ultra-diffuse galaxies in Coma. And then other people, Vandenberg and others, found thousands more in other galaxy clusters that had just been overlooked effectively. There were about a handful known before our paper, and then 6 months later there were thousands known. And so it's an interesting sociological story. You know, why are things missed that are clearly in data? I won't go into that. But in any case, we found them with Dragonfly because we were looking for them. That's just the essential, the essential reason why we found them. And so this is a comparison of an ultra-diffuse galaxy, actually the same one, Dragonfly 44 with Hubble, to other galaxies where they were all put on the same physical scale. Okay, so here they were all moved so that they are, at the same distance from us artificially, and so it gives you a sense of the size of these things, right? This big blob, and then that looks in its overall extent about the same as a big spiral galaxy, like M31, much bigger than normal dwarf spheroidals like Fornax, at the top, much bigger also than say M82. Which is a pretty small galaxy, but still. And so they look like dwarf spheroidals to first order. They have these sort of Gaussian profiles, very smooth, old metal core, but then far bigger, by about a factor of 10 in half-light radius. The other thing that you might notice here are all these dots in Dragonfly 44, and those are globular clusters. So that's the other odd thing about them. On average, there's huge scatter, but on average, they have about 5 times more globular clusters than other galaxies of the same stellar mass. So that became clear also fairly soon. Beasley et al. And Lim et al. Were the first to see that. And then, we and others followed up and confirmed it. So they have many globular clusters in general. Okay, so those are ultra-diffuse galaxies. Really nice, interesting. Here in this talk, the topic is dark matter. And these ultra-diffuse galaxies are really useful for constraining dark matter and measuring its spatial distribution. And the reason is it's nothing, sort of particular to ultra-diffuse galaxies or special about them necessarily a priori, but just the fact that they are big is a big help. And this illustrates that. So these are density profiles, artificial density profiles, obviously, of a normal galaxy and an ultra-diffuse galaxy with the same dark matter halo. And so in a normal galaxy, the center, the stars are mostly in the center of the halo, and that's where the baryons typically dominate. Like in the Milky Way, the baryons dominate out to about an effective radius. And in the center, the dark matter is completely subdominant, so very hard to measure. You have to go, classically, right? You have to go out into the halo to measure the dark matter. That's where you start to see the effects. But what happens if you spread out the stars, and so you have a much lower stellar density, but the same total number of stars, is that the dark matter dominates now at all radii. Okay, so even in the center of the galaxy, you expect the dark matter to be completely dominant. And so the motions of the stars or the gas or whatever you have in an ultra-diffuse galaxy should be completely dominated by the dark matter. And that means it's fairly easy to measure the dark matter in these systems on small scales. And that's interesting because there's a lot of dark matter candidates, like fuzzy dark matter, where the dark matter are these huge kiloparsec scale particles. There's the whole cusp core problem that's probably related to the ultra-diffuse, to the fuzzy dark matter. There's a lot of interest in the centers of halos and the dark matter distribution. And these ultra-diffuse galaxies are useful probes of the dark matter. But the key thing is they should be completely dominated by dark matter in the centers. That's the expectation. And so this just summarizes that. The challenge, though, is to measure it, because the light is very diffuse, by selection, effectively. That's what we've been talking about. And it means that you need to have, long exposure times, typically on large telescopes, to measure the kinematics from the stars. Or, as we'll see, sometimes you can use the globular clusters, the kinematics of the globular clusters, to constrain the dark matter. But that's a challenge, to measure the kinematics for these low surface brightness objects to constrain the dark matter. Now, the first paper we did on this in 2016, so a year after we found these galaxies, We went out with Keck and we measured the velocity dispersion, you know, with 33-hour integration with DMOS, very hard, and to see what the dark matter content of these things was. And so as you can see here from the title, we found a very high velocity dispersion of 47 kilometers per second, and then you can estimate what the total mass is. You know, within the half-light radius, you can extrapolate that using an NFW profile. And what we said in the end was that the total mass of this galaxy was about 10 to the 12 solar masses. You know, very, very massive, as massive as the Milky Way, right? And so we made this claim in 2016 that these ultra-diffuse galaxies, or at least this one, had the masses of the dark matter masses of the Milky Way, and that got a lot of attention. Because what we basically suggested here was that they started out as being Milky Ways, but then failed Milky Ways. They stopped forming stars where the Milky Way just continued. So something happened in the early life of these galaxies, that was the speculation, that made them, made star formation stop. Only 1% of the stars were formed or less, but they still had this huge dark matter content. So these very dark objects that are out there. Also, it would change the number of L-star galaxies in the universe by a significant number, right? Because these massive halos are rare, and all of a sudden we find these thousands of ultra-diffuse galaxies. If they're all 10 to the 12 solar masses, that has a lot of implications. All based on this one dispersion measurement for one object in the center. But this is what we found. And this is where this new galaxy back then came in, NGC 1052 DF2. The nice thing was about this object is that it's much closer. So the Coma cluster is 100 megaparsec from us. This galaxy is only about 20 megaparsec from us. And we'll talk about the distance later, the precise distance, but a factor of 5 closer than the Coma galaxy. So much easier to study, right? Everything is 25 times brighter. And bigger on the sky. So you can do things that you cannot do at the Coma cluster. And so we found this object, and here's our early HST image, 2 orbits of this galaxy. It's again a fuzzy blob, and again it has a lot of dots. These dots again are globular clusters. So here you can see how big this galaxy is. Now this is putting the 2 galaxies with the most similar stellar masses in the local group at the same distance. So to compare, right? Famous galaxies, NGC 147 and 185, satellites of Andromeda. This is what they look like compared to DF2, right? And very, very different. So again, this super spread out distribution that allows us to measure the dark matter. And then here are these globular clusters, this image is enhanced in such a way that point sources are emphasized. And you see these dots, not as many as in Dragonfly 44, but still many more than you'd expect for this stellar mass. And the other weird thing about this galaxy is that the globular clusters are very bright. So the luminosity of the globular clusters is about 4 times higher than the peak luminosity in the Milky Way. And the brightest globular cluster in this galaxy is as bright as Omega Cen, right? The most luminous globular cluster in the Milky Way, and often thought to be the core of a disrupted dwarf galaxy. So here we have a bunch of these globular clusters that are way too bright than they should be in this fairly nearby galaxy. So we thought that's great. This is wonderful. What this offers us is a chance to measure the kinematics from these bright globular clusters, right? Because they're relatively easy to observe. Because A, they're bright, and B, the galaxy is not too far away. So let's measure the velocities of the globular clusters and confirm that these things have Milky Way masses. That was the thought. Okay. This illustrates what we expected. This is what the velocity distribution should look like for a normal halo of 6 times 10 to the 10 solar masses. That's the halo mass that you expect for this galaxy if it was similar to the Andromeda dwarfs. If it falls on this normal stellar mass halo mass relation. I didn't put 10 to the 12 on here. That would be even wider. right? Because that's another factor of 10 extra mass. So it would be a factor 3 wider here. The distribution wouldn't really fit nicely on the plot. For a normal halo, we'd expect this particular distribution, and for the stars alone, if there were no dark matter, you'd expect the red distribution. And so what did we find? This. Okay, so this is a histogram of some sorts of the measured velocities, actually ordered by the distance from the mean velocity. And so all the velocities fall within this red curve. And we see an incredibly low dispersion, far lower even than expected from a normal halo, let alone for a Milky Way type halo. And so you have to realize that when we measured this in late 2017, this was a complete surprise and the opposite of what we had been expecting. Right? We've been promoting this view. These are failed Milky Ways, very important. Everybody should pay attention, and people did. And then we find the second galaxy we look at, and it's completely inconsistent. So what you can do is you can say, well, we were wrong, right? That's one way to go. Or you say, okay, we don't understand these galaxies, and you write a nice, FJ paper and where you explain how wrong you were and how we don't understand things. Or you do something else, and oh, this is the velocity dispersion first. Sorry, I'm skipping too far ahead. So here's the velocity dispersion. This is just to quantify what I just said. The dispersion is only about 6 or 7 kilometers per second, and the expectation from the stars alone is about 7. Right? So velocity dispersion is very, very low in this galaxy. Anyway, so what we did was this. We wrote a letter to nature about it. We said, hey, this galaxy has no dark matter. So first we had this big splash saying these galaxies are all, crazy massive and they're failed Milky Ways. And then 2 years later, we said, they actually don't have any dark matter at all. And it's no wonder that people were like, okay, these people are just seeking publicity and they don't, or they don't know what they're doing. So, I'll take that on in that sense. But on the other hand, what do you do when you find a thing like this, right? It really was kind of very, very strange. So we wrote this paper saying that this galaxy has no dark matter at all, or at least it's consistent with having no dark matter. I think we said something like it's a factor of 400 lower than expected, the dark matter mass, or more. So the claim then at that point, the claims were these, right? We said this galaxy is larger than any local group dwarf, very big. Then we said the globular clusters are extremely luminous, more luminous than in any other galaxy, by the way. People have used the luminosity of globular clusters as a distance indicator because it's so well constrained. And Diederik can explain to you why, right? There's good physical reasons why to expect that if star formation occurs in the same way in different environments, you expect that every galaxy has the same luminosity function of globular clusters. Now, there's an important caveat there. If star formation occurs along the same lines in every galaxy, and he has shown what happens if that's not the case, then you can shift the peak. But anyway, observationally, this was a unique object from that perspective. Then this claim about dark matter, little or no dark matter. And so the suggestion is then that there is a pathway of forming galaxies that's basically different from anything that we've seen before. It even calls into question what a galaxy is, because when we talk about galaxies, we usually say, well, you start with a dark matter halo, right? Then gas cools, you form a disk, you form stars, blah, 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 blah. We have this whole story about, what a galaxy is. And then there's there's deviations, like you can form in a tidal arm, you may be able to form a galaxy out of gas that was ripped out of a more massive galaxy. So there are some exceptions. But to find this sort of relatively isolated object without dark matter is very unusual. And what maybe got most people's attention was that we also said, well, it means that dark matter is actually a thing. That is, it's something that the galaxy can have or not have, right? That rules out classes of explanations for dark matter, in particular alternative gravity theories. On the scale of galaxies, there are problems with Mond and with emergent gravity on large scales and in galaxy clusters and et cetera, et cetera. But on galaxy scales, it's been extraordinarily successful. MOND, that description has just time and again shown to work. And in this case, it's a galaxy scale. It's a scale where MOND is supposed to be, ruling the roost, and it seemed to rule it out. And so people were not happy, to say the least. And so within a week, there was the first rebuttal paper. Pretty blunt. Current velocity data do not constrain it to like dark matter. Just say not in the title, right? It could have just said not. Anyway, it was Nicolas Martin who actually did a very careful analysis of the velocities of the globulars that we had measured, and showed that there was still room for, there's a large tail of probability that we had kind of ignored, and that the data were inconclusive according to them. But they were not the only ones. There was a lot of flurry of papers saying that we were wrong in many different ways. The only thing that the papers did not agree on was what way exactly we were wrong. But definitely the sentiment was that most things were wrong. And so we went out then in the next few years and did sort of the hard work to check everything, because those papers had a point, right? You do need to go above and beyond to substantiate a claim like that. So first we measured stellar kinematics. I won't go into too much detail here, but we confirmed the velocity dispersion that we measured from the globular clusters, but now from the stellar kinematics, similar to what we had done for Dragonfly 44, and we found the same result. Okay, 8 kilometers per second, where you expect about 30 for a normal dark matter halo. And Eric Emsalem, with a larger uncertainty with Muse, found the same thing at the same time. So there was that. Then the mass modeling is too simplistic, and so we did the hard work of creating an actual model where we used the globular cluster, individual globular cluster velocities and the dispersion as constraints, and made a generative Bayesian model to assess that. And Wasserman showed that yep, you essentially get the same result, an upper limit on the amount of dark matter. And just skip that for time, but that was the. I'm happy to go back to that if people ask. Then there were a lot of explanations that just said, there's something unusual about the orbit of this galaxy, about the orientation. Maybe it's a face-on disk, right? That would explain it. Very low velocity dispersion. It's exactly face-on, and all those globular clusters rotate in a disk. You might miss that. Or there might have been a really weird orbit, somehow, and you're looking at it from a particular viewing angle. And so there were a lot of these sort of tail of the distribution effects, where if you find one object in the sky with a peculiar property, it could just be that you were unlucky or lucky, right? And that actually is not representative of that galaxy itself if you looked at it from another viewing angle, or had more data. But that was resolved in sort of a neat way, and that is that we found a second galaxy in the same group with the exact same properties. So this is 1052 DF2, but the one I've been talking about, right? And I know this will be kind of jerking this simulation. Sorry about that. But then on the other side of the elliptical galaxy, there's another object, DF4, which is a splitting image of DF2. So it has it's about the same size. It's another ultra-diffuse galaxy. It has the same stellar mass, and it also has a population of extra-luminous globular clusters. Exact same thing. Same globular clusters, same diffuse light, everything the same as DF2. And then, so here are the globular clusters in this galaxy. They're more spread out than in DF2. That's why it wasn't very obvious until you actually measured the velocities of the globular clusters and found that they were all associated with this galaxy. Lo and behold, the dispersion of those globular clusters is only 4 kilometers per second. So the relative motions of the globular clusters, they're all essentially at the same velocity, 45 kilometers per second, which is also the group velocity. So another galaxy with apparently no dark matter, very luminous globular clusters, diffuse size, and everything the same in the same group. And that means you can't have two galaxies being exactly, face on or have some kind of very fortuitous orientation. And so that really resolved that issue. Then finally, a point that is correct, you know, and that we just missed, that is the folks who work on MOND quickly came out with several papers. You know, this is 2018 July, right? This was just 2 months, I think, after our paper. And there was a note in Nature too, in response to our paper by Krupa and company, that said that if in MOND, if you are close to a massive galaxy, you're no longer in the MOND regime. Essentially, the gravitational potential of the larger galaxy means that you are in the Newtonian regime. Don't ask me about the details, but you're in a Newtonian regime, and that means that you should actually not see a dark matter signal for galaxies that are very close to massive galaxies. So they've applied this, and that's been around since the 80s. This is not something they invented. That's a feature of the way gravity works in MOND. And it sort of works for Milky Way satellites that have, you know, kind of, there's a big debate about that I definitely don't want to go into. But they said, look, if DF2 and DF4 are very close to the massive elliptical, you know, within about 300 kiloparsecs, then this external field effect will lower their dispersion. And actually, this is exactly what you would expect, to see a low velocity dispersion for this galaxy. So they came back with this argument, which is a reasonable one. I just had no idea about this. When I wrote the paper, I should have asked them before publication, and I didn't. So that's what happened. So that was the other thing, that even the MOND claim was wrong, even if you took everything else as correct. Then the final thing, and this got a lot of attention as well. This is by Nacho Trujillo and Beasley and also Matteo Monelli, where they said, well, what about changing the distance to the galaxy, right? You assume that it's at 20 megaparsec. Well, there's not quite an assumption. It came from surface brightness fluctuations and a lot of other things. But anyway, if we maybe these galaxies are in the foreground, and if they're in the foreground, a lot of things get better. First of all, they get smaller physically, right? The physical size becomes smaller. The globular clusters become fainter intrinsically, closer to what you would expect for a normal globular cluster population. And even the dark matter constraints are less stringent, because now they're closer to us. That means they're intrinsically fainter. The stars contribute less to the mass, and there's room for dark matter. So they made this argument, well, what if you just put it in the foreground? And they did that in several papers, and you know, based on this argument plus what they claimed was the detection of the tip of the red giant branch in our 2-orbit depth data. And so the only way to resolve that definitively was we wrote a lot of argumentative papers about this, but the way to really actually fundamentally address it is to detect the tip of the red giant branch without you know, without a doubt, and to identify the red giants in these distant galaxies. And so we obtained very deep HST data, first Daniele et al., and then very recently Shen et al. This came out like a week ago, and we'll have a press release this week, I think, on Shen et al. Where with Shen et al., we got 40 orbits of data on DF2. So 40 orbits of imaging of this one galaxy, very deep data for a single diffuse object. And it's quite beautiful. This is the version that the ST folks made, which is quite astonishing. So now you see all those little red dots, right? So those are individual red giants in this galaxy. And I'll just zoom in on a little piece. So we detect now the individual stars, the individual red giant stars in DF2. What's interesting, by the way, is that every other galaxy you've ever looked at, we always have to say, oh, there's also the dark matter, right? In this case, what you see is what you get. This is it. You know, this galaxy is plain as day. It's like there's nothing missing. There's nothing, you know, that we're not seeing. But that's sort of a separate point. We see the red giant, so that means we can measure the tip of the red giant branch quite accurately. And that's what we did, or what Zilli did, rather. And what we find is, you know, on the right, you see the luminosity function here. The red is a model, the black is a data, and you can see how well the model goes through the data. And that's for a distance of 22 megaparsec for DF2, which is actually a little further than what we had been using, and definitely not 14 megaparsec. That would be the yellow luminosity function on the right, and so that is ruled out completely with these data. So the distance is done. That's definitive, unless you start to mess with the helium flash, in stellar evolution. But if you believe the triple red giant branch, then the distance debate is at least settled. So that's where we are. So I think it has held up. So most of this talk is a little odd in that we first make the claim and then talk about why we think it's true. But in this case, I think it was necessary, and we've learned a lot of things along the way about these systems. Yeah, essentially, this still seems to be the case, that these galaxies don't have dark matter. Interpretation, I won't say too much about it. We don't know. We still have no idea, really. There's a lot of ideas that have problems. To me, and I'm not just saying that because Diederik is staring at me, the idea that feedback from the globular cluster formation is central to understanding these things, I think has the most merit. The globular clusters certainly demonstrate that the galaxies were extraordinarily dense at some early time. Right, they're puffed up now, but they must have been extremely dense at some early time. So that must be an important clue to their formation. Most other things like tidal puffing and tidal dwarfs and just errors all have problems. There's some new evidence, a little bit from Dragonfly, where we discovered that both galaxies are tidally distorted. They have, they have distortions. This is a Dragonfly image. This is the HST image, and you can see by eye that the ellipticity changes at the position angle changes between these two images. And the interpretation is that the galaxies have such a low mass because they have no dark matter, that even though they're not directly impacted by any other galaxy, just the impact of 1052, this distant elliptical, is enough to disrupt them. So they won't live forever. They will actually be destroyed eventually in the tidal field of the group. And we see that process in action. And actually, the radius where this occurs gives you an independent constraint on the mass, turning that argument around. So that's what Michael Keim, who's another grad student at Yale, is working on. Now, and then the other really puzzling thing is, I mentioned that the distance to DF2 turns out to be 22 megaparsec instead of 20. And DF4 is at 20 megaparsec. And so there's a 2 megaparsec distance between these two galaxies along the line of sight. And that measurement is oddly precise. And that's because the data and the methods are all identical for these two objects. So even though the TRGB method is not calibrated to better than about 5% accuracy, we can measure this relative distance to to an uncertainty of about 0.4 megaparsec, which is about 4%, and 2%. Sorry, it's about 2%, because again, all the systematic errors drop out. So the yellow is DF4 here, and the black is DF2, and there's a clear difference in the luminosity function location. And so that difference immediately gives you a distance difference without any calibrations or theory of 2 megaparsec. And that's very, very odd. The radial distance is far greater than the projected distance on the sky. And at least one of the galaxies, and maybe both, are not even part of the group, are not in the virial radius of 1052. So they were either expelled, or they're falling in. But why would two identical galaxies fall in from different directions? There's no causality there that makes any sense. So this is a new clue that just came out again last week, and we don't understand it. So what have we learned then in the end? So these large diffuse galaxies are surprisingly common. They are very common in clusters, more common in clusters than elsewhere, although they also exist in the field and definitely in groups. And they're interesting. They're not just big. They have these weird globular cluster populations, many of them. And some have no dark matter, some have a lot of dark matter. there's this large variation in the dark matter properties, and we can learn about the dark matter in a unique way because they're not baryon dominated in the middle, or they shouldn't be. You know, DF2 is obviously. And so we don't really understand them very well. There's a lot of follow-up work to do, and maybe particularly on the theory side. I mean, observationally, what we have to do is simple. We have to look for more. We are doing wide field surveys with Dragonfly. We're imaging the entire Sloan area to create an archive that anybody can just go to any place in the northern sky and say, what is the low surface brightness emission here? Right, we'll publicly release it. We're sort of lacking money and manpower for that, but we hope we will get volunteers for people who actually run these archives, and that might be happening. You know, I think that'll be great. And then we'll find, like, are there such galaxies within 10 megaparsec from us? You know, they might be hiding in plain sight, but right now we don't have the tools to see them. And also specifically for these galaxies without dark matter, I should point out Guo et al. To 2020. They used H1 data and found the same thing, for that many galaxies have far too low velocity dispersions or rotation velocities than expected from normal dark matter. That needs follow-up work, you know, with VLA and other things. But I just want to point out that this may be a whole population that we're just starting to see. And I want to stick to the time. I have a few slides about narrowband filters, so if, that's the big upgrade to Dragonfly. But A, it's a different topic. I don't want to distract you, and B, I'd like to stick to the time. So, but if you want to know about it, then you can ask. And with that, I'll stop. Thank you.
Thank you. Right. Thank you, Pieter. That's a real mystery. I'm sure that many people wanting to follow up on this amazing detective work and these amazing observations. So I throw the floor open. Please put your hand up or type a message if you can't do that. Just while people are waiting, thinking about this, I mean, how precise is the sort of functional form of the dark matter distribution that you can ascertain in these galaxies? You mentioned you were doing some modeling on this, and do they have edges? You know, how far out can you realistically follow this in this profile?
Yeah, those are really great questions. We so the globular clusters trace the dark matter out to about 10 kiloparsec, which is really far. And the interesting thing is, because the dark matter content is low in DF2 and DF4, it also means that the virial radius is small. So, you know, like, you can constrain whether the galaxies have, say, a 10 to the 8 solar mass dark matter halo really well, because we're tracing out to the virial radius for that halo mass, which is something we never do normally, right? Higher mass halos are much harder to constrain because we only see the center of the halo, because the halos are much bigger. But so you get this very odd effect that when you derive a lower halo mass, your constraints become stronger for this, because of this effect that they're actually the halos are more compact. That means that you constrain them better. But in general, for the Dragonfly 44, I didn't mention that, but our initial result was wrong in several ways. You know, in 2016, it's true that the galaxy is massive, but it's not 10 to the 12 solar masses. It could be, it's within sort of 1 sigma, but the peak solution now with new data is about 10 to the 11 solar masses. Oh, and what we did there was we assumed an NFW profile, but if you allow a core, you get a much lower halo mass, you know, for the exact same data. What we did for Dragonfly 44 is we got beautiful spatially resolved data from the Cosmic Web Imager on Keck, which gives you spatially resolved kinematics, you know, 2D kinematics. And we integrated for 60 hours, some ridiculous number, to get radial velocity profile, Dragonfly 44. So the best constraints you can hope to get. we could even measure the H3 and H4 parameters, so the deviations from a Gaussian velocity profile. And but the results, I mean, I wrote a huge paper on this in 2017, huge, I don't know, 40 pages, not this little applet letter that we did before. And but in the end, with careful modeling, you couldn't say very much, because this issue with the degeneracy between a core and the halo mass is almost unsolvable. It just all, you know, in principle, the anisotropy, you know, could be constrained with H3 and H4, but even that didn't quite work. Like the values didn't really match any model. So it was a little frustrating, you know, but we did what we could, and in the end, it's just very hard. The way forward, I think, is stacking. Is actually to measure many galaxies and get average profiles that way, because the different effective radii constrain the mass independent of the anisotropy on different physical scales. So if you then assume that they all have the same halo, big assumption, you constrain the halo at different radii without the anisotropy difficulty. But that requires a ton of data. Bob and I are thinking of building a telescope to do that.
Okay. I'll maybe come back to that in the additional discussions afterwards. Ralph has a question, if I may ask him.
Yeah.
Okay, thank you. Thanks, Peter, for this fantastic talk. I think these are really interesting objects and very puzzling. I'm wondering what is known about the Staff mission history, whether you, with the photometric approach that you have, can say something about it. And by constraining this, you can learn something about the origin.
Yeah, absolutely. What we have are very good spectra of the globular clusters, so which give an age of about 9 billion years. Luminosity weighted age, and a low metallicity. Other people with Muse have, Eric Emsalem and company have gotten also pretty good data for both the diffuse light and the globular clusters and find similar ages, so old. The issue is that the blue horizontal branch is a big uncertainty in this low metallicity regime. So in the Milky Way, if you look at globular clusters with that metallicity, their integrated light ages are actually wrong. So you would derive an age of 9 gigayear, where the true age is 13 gigayear, you know, of Milky Way globular clusters of low metallicity. And the reason is that many have a prominent blue horizontal branch that's not included in most models. So we have a lower limit on the age of 9 gigayear. We actually have new HST ultraviolet imaging of the globular clusters to resolve that specific thing, to test what the blue horizontal branch is. But we're pushing the data and the models a bit far in this sense to constrain the blue horizontal branch with just photometry and an optical spectrum. But the short answer is at least 9 billion years. The problem is we'd like to know better, because 9 billion years is when the big elliptical formed, probably. You know, it's about redshift 2 or 3. That's when that, you know, this group was a mess, almost certainly. You know, the elliptical was forming, tons of gas streams, you know, merger probably going on. And so it's fairly easy to imagine that pockets of gas did something at that time, right? Whereas if it's 13 billion years, then they precede the formation of the group. And then you're looking at something primordial and a sort of a more fundamentally different mode of star formation. So this lower limit of 9 gigayear is tantalizing. We'd love to.
Do you know something about the radial dependence? I mean, these things are big, and you may have some spatial resolution. Is there some age gradient or things like that?
Not that we have been able to detect, no. You run into very subtle things, like the HST data turn out to have a flat fielding problem that we've spent a ton of time with the HST folks figuring that out. We thought we saw a big color gradient, but it turns out to be a flat fielding issue with HST. Yeah, no, they seem to be homogeneous as far as we can tell.
Interesting. Okay, thanks.
Sebastian?
Hi, Peter. Thanks for this really interesting story you told us. So as you know, I'm quite fascinated by the consequences of these findings, and in particular, the consequences for the galaxy population overall, and especially field galaxies, which are the dominant galaxy population. And so I was wondering if you had any thoughts on, I know that some people have looked at constraining the fraction of galaxies that have been missed in surveys. So how many do you think we're going to find when we have deep enough surveys, and whether this is going to be this is going to require us to revise the way that we think that galaxies form, or this is going to have important consequences for the field.
Yeah, no, thanks. And I should point out for everyone that Sebastian wrote what I consider the most, important paper on the interpretation of these things this year. Going to the globular clusters and as I mentioned before, that they are the key. I wish I had positive answers to these questions. We've not done the sort of thorough work, definitely not with the ultra-wide survey that we're doing, which is all of Sloan. But Shani has been working on the on a 400 square degree survey with very deep Dragonfly data, and there isn't that much. Essentially, it's not like the sky is absolutely filled with these very low surface brightness galaxies, and people have looked also, Karen Chenchev, using photographic plates and CCD data later. And it goes all the way back to Disney, who looked for low surface brightness galaxies and found a lot of spirals that had been missed. So my sense is that there won't be that many in the field. It's also related to the observation by Marla Jiha that isolated galaxies in the field, low mass isolated galaxies in the field, are almost always star forming. We don't know of a mechanism to turn off star formation in the field. We just published a paper actually on a rare, apparently dead galaxy in the field of 10 to the 6 solar masses. Eva Polzin was the first author, another Yale student. So I think they're pretty rare, but we really don't know yet. I suspect most will turn out to be in groups. Most dead things will turn out to be in groups. Star-forming things might be equally interesting, right? We're sort of weirdly biased with Dragonfly to look for the hardest things. Not that you asked, but the narrowband filters, will actually are optimal for finding low surface brightness star-forming galaxies in sort of the same way, because we're doing H-alpha. We'll be doing H-alpha surveys with sensitivity that's like 2 orders of magnitude better than anything that has been done. Sorry, a lot of waffle, but I don't know. And also the implications for galaxy formation. I do think it's important, but in some regimes, one object can be important. Like, ruling out Mond, you only need one object that's exquisitely measured. There's many examples like that, where, finding one Earth, right? And so I suspect it's more in that regime, that it demonstrates a pathway, even if that pathway is not the dominant one. It's going to be interesting for us to learn about initial mass function, star formation properties, perhaps even cosmology and dark matter. I suspect it's going to be more in that direction than that we have to have a complete overhaul.
Okay.
Thanks.
Okay, if I might just move on to one last question from Diederik.
Thank you, Richard, and thank you, Peter, for a really exciting talk. I think we're going to have fun continuing the discussion in a bit. So my question is about a result I had not seen. I find really interesting is this tidal perturbation that you see the 2 different contour levels you showed towards the end of your talk. I envision that in order to really rule out anything other than gravity, you would want to see that in different tracers, kind of. So towards the end of this question, I think it will link to the narrowband filters. But the first thing that is maybe a stretch is, could you potentially see this also in the globular clusters? I realize it's a small number, but I'm just curious if the distribution of globular clusters traces sort of the same shape, and which of the two contours. And then second, could you maybe do something with narrowband filters to try and select certain parts of the stellar population to basically try and answer this question?
Yeah, no, the distortions are interesting. We actually, in the Nature paper in 2018, I included a very vague paragraph because I was worried about the lack of distortions. You know, I calculated the Lagrangian points and I was like, if these galaxies have no dark matter and they are in the group, can they survive? That was the question I was asking. And it turned out barely. You know, you should have within like at 5 kiloparsecs or so, they should start to be distorted. And so you can call it a prediction, but in that paper, I noted that they really should be distorted, or you know they have enough mass to hold them together somehow. And so that's why we looked with Dragonfly. And I should say Mireia Montes also first discovered, you know, before we did, published for DF4 tidal distortions. And so we see it also around DF2, which you would expect. And so that we actually see them is encouraging. The weird thing though is with this 2 megaparsec distance between the two, at least one of them is kind of too far to be distorted. So now we have the opposite problem, that they're too much distorted, even with 0 dark matter. Anyway, happy to tell you more about it offline. The idea of tracing the globular clusters is really interesting. And I had the same idea like the week after the HST deadline, because what you can do is just with one orbit, right? You can pave a little area around each of these galaxies and look for a tail. You know, because even if you find one globular cluster, it's going to be significant because it's going to be brighter than what it should be. So you know it's not, you know, it's part of that galaxy. And then you can measure the velocity with KEK to confirm it, or with anything. So yeah, next HST deadline, I'll try to remember putting that in, because I think that's a great idea. The narrowband is mostly aimed at emission lines. You know, it's an ultra narrow H-alpha filter. You know, we have a trick to do that. There's no time to really go into it, but it's so sensitive that I think you can even do absorption work with it. So yeah, you can tune the filter. It's a tunable filter through another trick, and so you can tune it to the exact wavelength of H-alpha absorption, and then do off-band and on-band by tuning it slightly off and on, and it should be like a 7% effect in the filter. And so observable, and potentially you could do radial gradients that way. Yeah, we'll definitely look at the 1052 field with that setup, you know, as soon as we can. Yeah.
Okay, well, thanks very much. I have to call a close to the formal question session. And before we thank Pieter again, I'd like to announce next week's colloquium. So I'll just move on to the screen here. This is going to be again another form of very, very precise measurements, but going completely to the other direction of very high angular resolution, and we're going to have a great variety of physical results, I think, from that colloquium next week. So now I'd like to invite everybody to open their microphones and open their videos, and let's give Pieter a great send-off for this fascinating and very, very mysterious talk in terms of the topic that he has given. Thank you very much.